physicists, podcasters, they don't seem to understand that just because two paths are accelerating, right, towards one another, it doesn't mean the objects are accelerating. Yes, they're accelerating towards one another, but are they being accelerated by any force? If not, then they're still in an inertial frame. What's so hard? If you're not being accelerated, you're in an inertial frame. What is so hard? I don't care if you have a picture of something accelerating. I don't care if you see something accelerating by you because someone threw a ball or something that's accelerating. I don't care. If you ain't touching the ball that's accelerating, then you're not accelerating, okay? Just like the Earth when you're falling down. If you ain't touching the Earth, if you're not touching that frame of reference, then you are still in an inertial frame of reference. You have to actually touch, or you have to either be accelerated yourself or be touching, grasping on, holding on to something that is accelerating. That's the only way you can be in an accelerated frame of reference. You just can't have your paths, happenstance, coincidentally, cross each other a million years from now. And you're like, yep, that means I was in an accelerated frame of reference the whole time, even though I was at constant speed, straight line the whole time. It's just the paths we're crossing, you know what I mean? So yeah, this guy, when he falls in, his clocks are going to slow down so slow that it takes billions and trillions of years for even 1 second to go by. He doesn't get stuck on the surface like they're bull. He doesn't get stuck. There's a film and that's where everyone stays and they never fall inside. Blah, blah, blah. Yeah, right. No. That would mean that time stops. Time doesn't stop. It just slows down really, really slow. Okay? And you can't, unless you're going to live for 10 trillion years, you're not going to see it fall. So it's going to look like it's just standing there on the surface, but it ain't. It's just moving. It takes trillions of years to move 1 second. You know what I mean? So what do you expect? You think you're going to see it? No, it's going to look like it's standing still, but it ain't standing still. Okay? Inside the spaceship, where they're accelerating almost the speed of light trying to get away from this black hole, time's going around, it's just going regular. They're just falling. They don't see any time dilation at all. They just fall right into the black hole. That's it. They don't this time that like it takes a million years to fall in. No, for them, they fall in. It only takes them a second or whatever, how many seconds it takes, normally. It's just to us on the outside, those seconds takes trillions of years for us to see them. You know what I mean? That's the only difference, all right? But yeah, they would just fall into the black hole. Eventually, their acceleration, they'd run out of fuel, and then they would follow the geodesic into the black hole or whatever. But it's not because this fictitious gravity field that affects objects' time. No, it's because the object has to accelerate up to overcome the geodesic, and so therefore the acceleration makes them go faster, right? And what happens when you go faster? Your clocks tick slower. That's what causes the time dilation. Oh, why can't anyone see this? They got PhDs, some of them 2-3 PhDs, and they can't see this common sense. Let's go on to move into another example, and this is the example that this woke podcaster is going to give us. Don't get me wrong, this woke podcaster knows more about physics than me. I ain't saying I'm smarter than him. I'm just saying he suffers from doublespeak. He suffers from brainwashing. And I know it because when you doublespeak, you know that you're brainwashed. So let's go on to his example, okay? And he says that he's going to have a spaceship park, so far away from the black hole. Parking means not orbiting. It means he puts his thrusters on and he stays the same amount of distance away from the black hole. Let's say it's 1,000 miles, right? He has to have his thrusters on, though, right? Otherwise, he will fall. He will follow the geodesic, right? And he will fall into the black hole, right? But the ship doesn't do that. It stays at its same coordinates. So there's we all know that, right? We all know the ship would fall if he didn't have his thrusters on. So he has to have his thrusters on to stay still. And we know that's a rule, right? Just like on this hill. He has to have his thrusters on if he wants to stand still relative to the ground. You know what I mean? In the rest of the universe. If he wants to stay 5 feet above the ground, he's got to have his thrusters on, going the opposite way of the geodesic. Same here. He has to have it. He has to have his thrusters on. I didn't see the thrusters on in the video, but whatever. So he is accelerating. So that means this guy in the thing is getting a time dilated. He's getting time dilated. If this was Earth, and you could put a pole on it, and have a pole come up here and have a clock in it, the clock on the pole and the clock in this spaceship will be time dilated, running at the same exact rates. There will be no difference. You won't be able to tell the difference. So, because the further away you get from the black hole or the planet, the less you have the space-time being accelerated down. You know what I mean? It doesn't accelerate as fast. That's why you're. So if you have a pole that comes all the way up here, if this was Earth, you know what I mean? The acceleration here isn't the same acceleration as down here when it comes to the space-time being accelerated down, right? And you can say, because of relativity, if the space-time is being accelerated down, you could just say, but from your perspective, you're being accelerated up, you know what I mean? Or from space-time's space frame reference, you're being accelerated up. You know what I mean? So this guy does get time dilated. Does this guy? Let's say that, he lets the guy fall out of the spaceship. Let's say this guy has a little box he's in, right? So he has a ball there, so he can see if the ball is floating, and he can do little physics tests to see. And the whole time he's falling, there's no time dilation. All his clocks in his box, they're all moving at the same rate because there's no acceleration. You can't have time dilation without, acceleration, right? Okay? He is inertial. Okay? Everything floats in his thing. We can all agree that even this woke physics podcaster is going to agree. This guy is going to be floating in this box and the ball's going to be floating there too. What's the test to know if you're in an inertial frame? Oh yeah, you hold a ball out, and if it floats, you're in an inertial frame. Oh, the ball floats. But he's saying it's not an inertial frame, and it's an accelerated frame. Double speak, double speak, double speak. Okay, well that's double speak. Okay. So this guy is standing still relative to space-time. Guy is accelerating relative to space-time. This guy is accelerating relative to space-time. Yeah, the people who are accelerating relative to space-time, they're getting time dilated. The one who is standing still relative to space-time, he is inertial. He gets no time dilation, right? And if you think it isn't the space-time that's accelerating down, you still, for some reason, think that it's the ball or the spaceship or the spaceman. Look at this graph right here. Okay, this is their graph, right? They draw these geodesics. They put A, B, C, D, E on the graph. They say this is the time or the ground. They say that this is their thing, man. Okay, and I look at it, and what do I see? What do you see? You see that the ball. Okay, because this axis is the time axis. We wouldn't actually see that. We would just see this, right? But you can see the ball never moves. It's at E here, right? It's at E here. And look at what happens to D. D accelerates to the ground. C accelerates to the ground. B accelerates. They all accelerate. By this point right here, there's no such thing as A, B, C, and D coordinates. They're inside the Earth, right? They have accelerated. I can plainly see. This. All these dots are spatial coordinates D. And I can plainly see that spatial coordinates D has accelerated to the ground. I can plainly see spatial coordinates C, because every one of these dots is, I can see it. Why? How can you see that on your own graph and then say, no, space-time does not accelerate down, it's the object. Even though I can plainly see the object kept its spatial coordinates. It never moved. It just floated there. But what I do see is, right, the ground and you relative to space-time have accelerated up. Because this man over here would be over here. His head would be at C. Spatial coordinate C. But now it's not. It's like it's spatial coordinates, what, HI, something like that? Spatial coordinate C is like down in the center of the Earth. So I can plainly see from their graph, if I showed this physics guy that we're going to watch soon, if I showed him this graph, he'd say, yep, this is spatial coordinates D, this is D, 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 this is E, this is C, 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 this is B. Yeah, yeah, I see how the spatial coordinates are dropping, accelerating to the ground. And then I'll say, oh, so space-time is accelerating to the ground? He'll say, no. He will double speak me, if you can believe it or not. And I could see plainly, if I take out the time thingy, right, I can see E, spatial coordinates E, is accelerating to the ground. The ball is keeping its same spatial coordinates. It never moved. Relative to space-time, it is just floating there, doing nothing. It has not been accelerated in any way, shape, or form. Okay? And I want you to imagine now, you're out in space, right? You got this, ignore this blue part, right? You just have this red ball and it's inside of a spaceship, right? But there's no thrusters. It's going 50 miles an hour, right? So it's gonna go on a straight path, right? It's in flat space. There's no planets around, nothing that's gonna be gravity or anything, you know. He's out in the middle of nowhere. We would all say, well, oh, he's traveling in a straight path. He's going 50 miles per hour, constant speed. And everything in his spaceship floats, right? We would all say, oh, that's an inertial frame. And what if I said, well, 1,000,000 miles away from this spaceship with the red ball in it, I got a blue spaceship, and it's got a blue ball in it. And it's moving at 50 miles per hour, and it's going, and I didn't show you the rest of the line. And I says, look, he's going in this direction. No rockets, no nothing. And I'd say, is he an inertial frame of reference? You'd say, yeah, he's going constant speed, constant velocity, constant direction, same straight line. Everything in his spaceship floats, you know what I mean? And then I'd say, well, okay, well, then I show you the rest of the blue line. And I'm like, well, look, and these are 1,000,000 miles apart, right? And this intersection is 1,000,000 miles away from either one of these two people. So they're not causally, you know, there's no gravity seeping over or whatever, right? And then I said, look, their paths intersect. Does that mean now that this guy is an accelerated frame of reference? You'd be like, no, that's insane. They're 1,000,000 miles apart. Who cares if their paths intersect? That doesn't matter. But then what if I said, oh, well, look over here. It's a mathematical law. It has nothing to do with physics. If you have two lines that are, you know, smaller than 90 degrees, they intersect at an accelerated rate if you follow those paths at constant speeds. Meaning if this ball is going 50 miles an hour and this guy is going 50 miles an hour, and you can see I split it up here, right? The angles are equal, you know. I split it up into hours. Here's 1 hour, 2 hours, 3 hours. Look what happens the first hour. He's moved over that much. Look how much he's moved over then this time. Now he's moved over even more. He has accelerated his path towards, both of them have. This blue has too. The blue has accelerated here, here, and then here. The same but opposite way as the red did, right? I'd say their paths are accelerating towards each other. Now does it change? Now does this red ball magically turn into an accelerated frame of reference? You'd say no, because they're 1,000,000 miles away. They don't know each other. Nothing's happening between these two people. It's just their paths are accelerating. They aren't really accelerating. Yes, they're accelerating towards each other, but they're not accelerating towards each other because they're being accelerated. They're accelerating towards one another because their paths just so happen, you know, it's just a happenstance that their paths actually cross. And they, you know, their paths are accelerated towards one another. You know what I mean? There's a difference between having your paths accelerated towards something and actually having you accelerated towards something. You know what I mean? But we can all see here, if these are 1,000,000 miles apart and that's 1,000,000 miles apart, that just because these paths intersect in an accelerated rate, it doesn't mean that either one of these balls are accelerated. Neither one of them are accelerated. Yes, they are accelerating towards each other, yes. But neither one has been accelerated to do that. They just had their paths just by coincidence, just by happenstance. Their paths that cross each other a million miles away.